So we will continue now with the presentations. Okay, so we will start by the first presentation. The title is Acquiring and Analyzing Data from Arduino-based Experiments. It's from the group team from Romania. I don't know if the group from Romania is already there. Oh, you're there. Oh, yes. Because it's, sorry by my confusion, it says here online. Only Petroni will be only online. But will she talk?
She will talk.
So our teacher will explain the project online, and we're going to build it. And then if you have questions, you can ask us.
We then we have the technical activity that we made for the project, for the same project that is the host of this event. So when my students will want practical work, I will try to present through some for this activity that we have. Our proposal is for a new method that can be developed for physics labs, but not only for physics labs. Method that we use Arduino and of course sensors for collecting data, because sensors, if you know, the main reason for their existence is to collect data and to work with the data. So why we intend to use this? Because for the project, as Professor Paulo explained before, the main reason of the project is to find new methods for working with students for STEM, but not only for STEM, but especially for physics, because the majority of the participants of the project are physics teachers. If you don't hear me, please tell me, because I'm not sure that you can hear me. Thank you very much. So, these activities that we propose that we want to show you are under the main objective of the project, that is innovation for studying STEM, in particular for physics. It is something that we think for many years, this part. It was acquiring data for a practical approach based on the Arduino sensors is something very, very new for us, for you as teachers, and for you, is of course new for students. What are the prerequisites for this proposal? Many of them are based on the realities in our schools. Perhaps for you, for some of your schools, it's not the same, but for us, physics classes and laboratories have something that are not quite well related with the reality and with the expectations of students. The majority of our laboratories have some materials, general endowment that is equipped with some devices that are not well accepted by students. There are many of them out today. There are some equipment that are not usual for students. They will need some of these only in laboratories. So it is the reason because we try to find some other alternatives for this. The problem for school is that we have not enough money to get all these the equipment for laboratories to the novelties of what the students can find and can buy this year, or with the equipment that they will use in everyday life. And another problem that we have for the majority of students, the laboratories that we develop are traditional laboratories, does not permit for them to develop their skills that they will use after that. For this project, we developed two activities that are under these circumstances. The first one was the project that we developed for the mobility that were in Valentino in Italy, and among with collecting data from other applications that are free to be used on digital devices, on phones that the students have. It is another way to collect data from Arduino and from sensors for digital analysis of the movement. The second one that we propose for the mobility that is in the last day of the mobility here in Maya, in Portugal, sorry, is quite closer to the team because it's based on collecting data from a circuit that uses, as you see, Arduino, and of course that uses sensors. This part, the second part, that my students will present to you, I hope that now they recreate the circuit, is something that wants to connect the practical activity, the practical applier for this circuit, and of course that has a part that can be used mainly as practical experiment for something that students can meet in the real life. We intend to create sonar, Arduino-based sonar, that will have not only the sensor that we see, it is ultrasonic sensors, but also based on the data that the Arduino received from the ultrasonic sensors. We made two possibilities, safer or not safer. Safer is, as you see, it is a green LED. The green LED we indicate that the distance between the sonar and the object in front of the sonar, the detected object, is greater than value that we intend to put, and if now the red LED will indicate this, and the buzzer will make a sound that will inform that the distance is not safe. This part was designed because we think that both those who see and cannot hear, and those who can hear but not see, to benefit from the same image, the same circuit that we make. Of course, which are the steps? This is an important part, important steps for the method. To make the circuit, of course, we will use elements and we will use Tinkercad to create the circuit, to see if the circuit is working, and to create using Visual Blocks or C++ or Java or something else, create the code that will be after that uploaded to Arduino. The advantages for this after that for visualizing the data, sorry, will be based on data streamer, that is an add-in for Microsoft Excel, add-in that can be downloaded freely from Microsoft. The advantages that we took from here is that data from sensor come accessible, affordable, and that can be applied for a variety of applications. Of course, this data streamer is a version for serial monitor, but has some advantages. If serial monitor can show you only the data in real time, in the working process, this data streamer allow us to collect the data and to put them on a special file that can be analyzed by different persons in different times. We want to remember the steps for collecting data. It's similar to Arduino IDE, more or less. After we will install this add-in on Excel, we can connect the Arduino Uno circuit via the laptop to the data streamer, and we can pick the data that the circuit will give to us. There are some limitations, some default for this data that we can receive, but we can manage to change something using the interface given by the data stream. Usually, all of these files can be saved and can be saved by default on the screen, on the main screen of the laptop, and after that they can be analyzed by different methods that we can have. It is possible, if we want to send more than one column of data, to work with more than one sensor, and each sensor to send and for us to collect this data, send it by many sensors at the same time, using some code like the one that you have on your screen for the moment. It is something that we can, after that, we can analyze using the functionality of Excel. Of course, we prepare this part because we even can transfer, if we don't have a special Excel, we can work on Drive, and after that will be easier for everyone to discuss on the data that will be collected. I don't want to borrow you because the method it is at the beginning. We try to develop other circuits and other sensors, and of course, because for us it is only the beginning of using Arduino in school. It is not in our curriculum. We can pick up different other proposals that are on the internet. Using our sensors or the sensors that we can afford to create circuits and to collect different data that can be after that analyzed. It is an alternative cheaper alternative for those who don't have well-equipped laboratory. A special thanks from my part to these three guys that you have in front of you. All of them are the heart of the project, of this part, because they try to find, each of them, to find a solution for our different problem that we need on our way to develop this matter. Thank you once again, and I hope that we will present other data sooner. Now, present you what they did.
Yes, very good.
Okay, so this is our sonar. As you can see, the servo motor rotates the ultrasonic sensor at on 180-degree angle, and when detects an object, the red turns on and the buzzer starts beeping. Yeah, it's like a car sensor, you know, when you go backwards and it starts beeping. Proximity sensor, yeah. And that's it. The Excel extension that Petronia told you isn't working on this laptop. We don't know why. Maybe because of the Excel version, but something like this. No, we don't install the extension.
Okay.
Run. Okay, so this is the code. Monitor. Monitor. Okay, so as you can see, it records the time, the angle of which is rotating, and the distance of the objects that it detects. And with this data, we can import it into Excel, and then we can use it, analyze it, yeah. Okay. And that's
So now, if you have any questions
yeah.
on the group or the teacher? No? Then you can ask in Portuguese and then we can translate, okay?
I have questions, but I can't wait my turn.
No.
Okay, Excel here didn't work. That happens. I know that happens. I have been there. But when you were doing the project for the first time, was it easy to use, to combine both of them? There were troubles. How easy or difficult was to combine Arduino with the Excel add-in?
So to combine them was pretty easy. Like first you wanted to make a radar screen, you know, but the code was too complicated and couldn't finish it in time. So we stick to Excel data, analyze, and because it's much easier.
So anyone else, any questions? So because of time, I think we can call the next group.
Once again. Okay, so let's go on and move to the next group. So the next group will be remote control Arduino car. It's from one of the two Turkish groups. Not there. Remote control Arduino car. Not yet. And what about Smart Chicken? Smart Chicken Cook project.
Hello. Welcome to the board. All right. Welcome. I am the secretary. Yes, I am. And even though you started the correct time, hold on. Hold on. Hold on. Give me one moment.
Okay.
All right. Now, is everybody ready?
Now the presentation is online. So it's Smart Chicken Cook project. It's from Turkey. And you may start.
Right now, I'm doing the Arduino car first.
Sorry?
Right now, I'm doing the Arduino car first before I start the Chicken project.
Okay, doctor, you can stop whenever you want, okay?
Okay, I'm doing the Arduino car first. Correct. Anyway.
So I'm sorry. It's remote control Arduino card.
Yeah.
Okay. Thank you.
Anyways, welcome to the first Science Connect Multiplier event. Teaching of Sciences, a challenge to overcome. My name is Tarkan. On behalf of Team Turkey, I'll be your next presenter for the Remote Control Arduino car project. We decided to build a remote control Arduino car as our project in order to combine Arduino technology with science. We use as material mostly electronic parts. As you can see, these electronic parts consisted of an Arduino board, engine with wheels, an engine driver board to help control the engine wheel, cable, a power bank as the power source, a handheld remote control, and IR sensors. We use the program Tinkercad to create the shapes of the body for the car. This picture was used as the template to make the body of the car. We were able to use one of our school 3D printers in our school 3D printing laboratory to print the body of the car. To make it easy for all the Reference Plus students, we created an instruction manual showing how to connect all the cables, Arduino board, motor driver board, power bank, and engine. This picture is an example showing how all the materials were connected to each other. This is how it was shown in the instruction manual. To prevent students from making mistakes while trying to write the code for the Arduino, we provided them with their already written program, and we simply sent it to the student PC automatically. At this point, we began to show how to perform the experiment by showing the students the videos we had taken of the Arduino card. We used a wooden ramp with a total of 3 different incline positions. Our first test position was done with the ramp at a flat position. The car's speed remained constant during this test. This video shows the test. As I demonstrate to you, you see that, right?
Yes.
Good. Here's the one with the 4 blocks. For our second video, we made 4 bricks to achieve a specific height. We used a total of 4 bricks to raise the ramp. Then we ran the Arduino card to see what would happen. This is our second video showing how the car speed is affected by the height of the ramp. As you saw what it did. For our final test, we raised the ramp using a total of 8 foam bricks. This was the maximum height of our test. As you can see, the Arduino card was able to go up the ramp using the 3 different levels of height. The 3 different levels of that height of that were used where 0 or 5 levels. Then a total of 4 bricks were used for our second test. And finally, we used the maximum of total 8 bricks. Once our video data was gathered, we proceeded to enter the car's weight and the length measurement of the wooden ramp in the tracker program. This information is required in order to be able to take the necessary measurements for the tracker program. These follows show our test results using the tracker program. We learned the Arduino card's speed was affected when the ramp was raised at a different height position. When the car lands on any ramp height, the car's speed will slow down at any angle due to its weight and friction from the incline. When the car runs without any ramp height, the car speed is constant and there's no reduction of speed. There is a formula used to calculate the velocity of an object. This formula, as you can see in the picture, shows the velocity equals distance divided by time. We were able to improve this formula applied to our project by using the results of the tracker graph speed outputs. After finishing our tracker program test results, we proceeded to find out the main question. If I raise the ramp, will the speed of the car slow down? We learned that the speed of the car is affected by the change of the ramp height position. We also discovered Newton's second law of motion was proven within this project. The law strikes that every object, like our car, persists in its state of rest or uniform motion in a straight line unless it is compelled to change that state force impressed on it. After completing the tractograph analysis, we reached a conclusion for our project. By commanding different actions to compensate for the vehicle's increased speed, it shows in the tractograph how Newton's second law of motion is supported. And now we have reached the end of our remote control Arduino car presentation. On behalf of Team Turkey, thanks for listening. At this time, if anyone has any questions or comments, please feel free to share them with me. All right. Now, does anyone have any questions?
Yes, there is any questions? Questions?
All right, tell me.
One question, someone?
So, are you hearing? Yeah, are you listening to me? Yes. So what was the most challenging thing in this project?
Oh, for the most challenging part,
Yes.
I mean, although for me, I took part on the tractograph part. Unfortunately, I don't know which one was the hardest part, but I'm pretty sure it was when making the Arduino or trying to build it.
Okay, thank you.
Any more questions?
So, now, I think you will start the Smart Chicken Coop project. Is that right?
All right, I'll get it ready. Just
Yeah.
give me a moment.
Okay, when you're ready.
Between your component and your Arduino software. At the same time, we were working with Arduino. The Autobot procedure was also being done. The Autobot procedure was going to be the one to provide the information needed to be used in the tracker program. We decided to take an extra chicken coop template to use as a display and demonstrate how to use the Autobot for the project. This photo shows how the display cardboard looked like while explaining the procedure. Once we performed our test by taking video of Autobot and using it with the tracker program, we were able to get our results. When the Autobot procedure was finished, we concentrated our efforts with the Arduino procedure in the box. In the photo, you can see a couple of different building stages of our box. Just like in the Autobot procedure, to save time and prevent mistakes during the assembling of the Arduino component, we decided to make an instruction manual for all the groups of students participating in the Erasmus Plus project. This photo shows how the second instruction of the manual was displayed, and also it shows detailed pictures of the connections with the Arduino. We also decided to provide the code for programming for the Arduino to make it easy for everyone. Here you can see what our instruction manual looked like after it was finished. The last components for Autobot in Arduino were the standing bracket for the smart meter and the smart door. This photo shows both of the special brackets used for the smart meter and the smart door of the chicken coop. Once the brackets were made, we gathered all of the cardboard templates for all of the groups, all of the necessary components, and then prepared it all for the trip. This project taught us the importance of technology and science working together in order to achieve advanced life. When both science and technology are used together, the possibilities of progress are unlimited. Thanks for listening. We hope you enjoyed this presentation. Sure. Thank you. Now, is there any other questions? And also,
Questions?
Question?
for
No?
surprise, it's me. And I mean, I have high hopes for everything in ninth grade. I've been working on this. I made the logo to fulfill the project to be what it is. And we've gone so strong to achieve goals to get good results for our country, for everyone, and for the world. We're thankful for you to have this presentation. Now, any questions for the project?
Just a moment. Yes, actually, I have one question here. I was wondering, I thought it was really nice. It's nice to combine Ozobot and Arduino. And my question was about, did you think about another project that could also combine Arduino, Ozobot, and eventually Tracker? That's the first question. I have a second one after that, if no one else has questions.
Okay, unfortunately, at one point I didn't understand one point because there was some kind of like a connection loss. I mean,
Yeah.
can you at least repeat it? And
Yes.
can someone type it in the chat to show the question that you asked?
My question was, besides the chicken coop, did you think
Yeah.
and did your students think about another project also involving Arduino, Ozobot, and eventually Tracker?
No, I don't think.
Okay. And the second one, you said in this presentation and the last one, you gave everything to the students. Did they have opportunity to create a little bit, to improve, to change? How was that dynamic during the project?
Oh, did your students think about other combined projects? Well, needless to say, for any project is kind of tricky. I mean, for the smart chicken coop part, I mean, even though I also happened to came up with an idea about the Autobot in check costume to have to give more life and I know this is kind of a tricky question and I was not expecting about that, but all right. For the combination of the project was color codes. And importantly,
Yes.
the most importantly, the program and the bot. Yeah, and the bot. Program and the bot.
Okay, thank you very much.
The program and the bot. Those were the most important things about combining them. You have to use color codes for the Autobot, to read them, then expand. Repeatedly.
Okay, thank you very much.
Okay, Patrick.
right,
Thank you.
then,
Come on.
Marisa,
Come on.
here, come on.
I think he is not here. Jesus. Okay, so I am Ioannis Tsiamouras, the representative of the Greek team, and I'm here to present to you a physics simulator, which is based around throwing objects. Now, this is how forces and speeds are depicted in an object during this course. This is an example where we have no starting height. In all of these examples, the error, the drag, and
Your resistance are considered to be minute and we do not take them into account. So this is a depiction of the program. I'm going to show you the program itself later. But first, by pressing the green flag, we are presented with some planets. Now, we could do this because we use the variable to change the acceleration of gravity. Of course, all those are going to be explained better later. So after that, there are requested some values which you will have to input so that the program can calculate some numbers that you will ask later, and that it will present the movement of the object. Here are the options available for everyone using the program. So range, which is the maximum horizontal distance, maximum height, which is self-explanatory, and the next four are actually position, height, and speed, depending on a certain point in time, which is not explained really well in the description here. So these are parts of the code. As you can see, it's a really long program. It's even longer than that. This is actually half of the code, even less maybe. And now I'm going to get in depth with the physics of this project. Now, first are some principles that we use. Now, in kinematics, which is the part of physics that revolves around moving objects, we can describe movements by using the movement of the object, and all that we can describe them using these formulas. As you can see, since we do not have a straight movement but a curve, you can see the cosine and the sine in the formulas. So here we can explain why we could use multiple planets, since G is a variable that comes from the mass of the planet and different other variables. It's something that is not stable in every planet. For example, the moon has around 1/10 of Earth's gravitational acceleration. So by altering the G force, we could simulate the direction of the object being thrown in different planets. So here is the formula that gives us the parabola, where psi 0 is the starting height, theta is the angle at which we throw the object, G is, as explained before, the gravitational acceleration, and always the initial speed that the object may or may not have. So, as it is explained below, this is what we use to make the graphs, and as I will explain later, the Ozobot will track now. So this is a graph. We decided to use Ozobot to follow these graphs because the Scratch program was a bit inaccurate due to visibility. We had to make everything visible, and it wasn't very good for the user. It was hard to understand what was going on. So we decided to add the more practical part, the Ozobot, which was follow graphs now. There's an issue about the two. The Scratch program gives great the speed and acceleration of the object, while the Ozobot gives a perfect representation of the trajectory. Now, so for the program to be perfect, it needs to be a combination of the two. This is also another example. In both of these, you can on the bottom see the values used. For example, 45 degrees of angle, 20 meters per second as a starting speed, and 4 meters height. And here, 60 degrees angle, 20 meters per second for starting speed, and 0 starting height. Now I am going to present the program. So, as you can see here, you can see it. I think we'll stop the presentation. So this is the start of the project. When I click the green flag, I'm going to be asked which planet am I on, basically. So I will choose Earth for this example. And now I must some values which can be obtained from a tracker program, as we explained in our abstract. So basically, if I throw an object in real life, I don't know the height at which it was thrown, the angle, nothing. So you can use a tracker program so as to calculate these values, and then here the Scratch project make the calculations for you, show you the simulation and all that. Also, you can compare the outcome of the throw of different parts using the Scratch project. So I'm going to use one of the examples from the PowerPoint, which is going to be 20 meters per second, starting angle of 45 meters and a sound height of 4. So now I am asked, what do I want to calculate? For this example, I'm going to use the range, the maximum distance the object will reach. So after pressing the number 1, I am asked to press space. This is because due to Scratch being able to convey information using that little thingy on the top, we need to make sure that the user is concentrated on the program. So if I press space, it's going to tell me the range, which is always calculated in SI. And then it's going to show the fall of the start. So as I explained before, it's not really accurate because we had to make it easy for the user to see and understand how speed changes. And that's why we can keep them the osmotic rate. Now, I am asked whether I want to calculate something else. I'm going to put yes here so as to show you one of the 4 last ones. So I'm going to pick number 4, random, for example. Now, because I can possibly know at what time it will reach the ground, I am shown at the top that at 2.6 seconds it reaches the ground. So I can pick any value smaller than that. For example, 2 seconds. And now when I press space, it's going to tell me how high we were at meters. Okay. So this is basically the program. After pressing the no, because we don't want to calculate something else, the credits are going to roll. And yeah. And that was our project. Thank you very much. Now, any questions?
Questions? What there at this moment?
So you said that the Scratch program is a little, it's difficult to draw an exact line, but the line that we saw, was the program doing it, or you had to make it?
Look, this is a bit of a misunderstanding because drawing the line is actually quite easy. The thing is, keeping an analogy similar to real life is really hard because space is really limited here. It's not like I can move my hand or something to show you actually how the object will move. So in order to avoid hitting on the border and actually making the whole movement visible, we had to alter some values. That makes it a reliable source at counting distances, basically. So as I explained before, speed and acceleration was what we were going for this class, actual distances.
Thank you. Any more questions, please? So, one question more.
It's not a question, it's just a challenge for you guys. Maybe you can give the same initial conditions and maybe you can make the output of the trajectory of the ball by choosing the Earth or Mars at the same time.
Oh, you
That
want
will-
to show up?
You have it.
Yeah, of course.
When I want two plants at the same time.
Oh,
That's
you can do that.
I like your project together. I like your project together.
It could be another project, but this one cannot do it at the same time.
It's a challenge.
Yeah, maybe next time, I don't know.
Okay, let's go to the number one, please. One more time.
Any more questions? No. Yes.
Hello, everyone. We are Science Connection participants from Latvia, and now we are going to present to you our project, Intersection Simulation, using Arduino Uno and Azubot. The goal of our project was to combine electronic capabilities of Arduino Uno program and mechanical capabilities of Azubot. The project aims were to show traffic simulation. We created crosswalk and sidewalk layout on paper. Using FDM 3D printer, we created small traffic lights, then put LED bulbs in them. Required components for this project were microcontroller, Azubot, jumper wires for Arduino, crosswalk and sidewalk layer lights for Azubot movement, traffic lights with red and green LEDs, ultrasonic sensors, and buzzer. Our team considered this project can improve safety of pedestrians near the roads using modern electronic components. Technologies used for this layer creating can be adopted in similar situations in real life. Another case of usage is functions for disabled people, especially for blind ones. Buzzer inform blind people about a safe possibility of road crossing.
So, to create our projects, we have chosen Arduino Uno and Azubot Speeds platform. Azubot simulates pedestrian, which is cross the roads, person who cross the roads. We used different Azubot color combinations, so you can see it on our real layout. Here is the black line, Azubot's movements trajectory, and some Azubot's colors, red, green, and blue. So the bots using it reads it, and slows down or go faster. So at the same time, all connected LEDs and ultrasonic sensors interact with Arduino. Arduino changes LED signals, gets values from ultrasonic sensors. To create program part of our project, we use Tinkercad. Tinkercad is an online platform where we can use blocks programming and also make circuits like this, where it's Arduino, whiteboard, two ultrasonic sensors, and two LEDs, which is our traffic lights. So this is our virtual layout, and this is our real layout. This is video how our project works. Also, bots begins to move slowly along the given trajectory. At the same time, turn off the sound because it's really better. As bot begins to move slowly along the given trajectory. At the same time, ultrasonic sensor number one. Let it be number one. This one, which is connected to Arduino Uno, and measure distance to other bots. When the robots gets close enough, like it happens now, and turn to cross the road, Arduino switches traffic lights number one. These ones from red to green and activates the buzzer. During the bot finishes or crossing the road, ultrasonic sensor number two, which is here on the other side of the road here, which is also connected to Arduino, turns traffic lights number one to stop lights, red lights. And when other bots approaching to ultrasonic sensor number two, to this one, when it gets close enough, it's then triggered and Arduino switching the traffic lights number two, it is this one, on the green and turning on also buzzer. After other bots crosses the road, it keeps moving to sensor number one. And our project repeats, project proceeds cyclically. So now I can show you our Tinkercad project. Here is it's loading. So here again, we have Arduino, which is connected all our equipments like LEDs, ultrasonic sensors, and also we have here breadboards. Here we used resistors, 220 ohms to connect LEDs, and yeah, this is how our virtual layout looks like. So, but the boards is done using blocks, using block programming, which we can find using Tinkercad. So we have only two variables, ultra one and ultra two, which is distance in centimeters to ultrasonic sensor. Yeah. So this is our project always. Which we download and upload it to Arduino using Arduino IDE. Yeah, and now this is our real layouts. So here we can find movement trajectory for the bots. Also, all components from our virtual projects. For example, yeah, ultrasonic sensors, LEDs, traffic lights, which is printed on 3D printer. Yeah, it works like this. Only here we can't hear a buzzer because we turned it off. But yeah, but it is possible to use in our projects. So we have some problems with our layouts, with our paper when we draw also what's moving trajectory. So yeah, this looks like. Thank you for your attention.
So we are a little bit behind the schedule. So if anyone has one question, please, I will not ask anything right now. Anyone questions? No questions? Okay. I think we have a coffee break right now, right?
Yeah. We shall have a short coffee break, 15 minutes, okay? And then we will return for the final oral presentation. Just one remark, please. For those who did not sign at the entrance, at reception, please go there and sign the papers. Para aqueles que não assinaram os documentos no início desta solução, por favor, vão à recepção e assinem os documentos, tá bem? 15 minutos para o coffee break, já sabem a data de si.
Coffee break, if you guys don't know, there is a,